Everyone, good morning. Today we will discuss about the stacking fault. So stacking faults are basically the defects, and it is basically the distance between two dislocation partials. So distance between any two dislocation partials. So this is the distance between any two dislocation partials. Now, this is the stacking fault width, that is the stacking fault width, that will decide how easy a material can deform. So a stacking fault width basically decides mode of deformation. How the material can deform, it is decided by the stacking fault width. Now, whenever we have cross slip, that is cross slip, in the cross slip, two partial dislocation, suppose one dislocation is there, another is here, one partial dislocation can merge together to a complete dislocation. So this is the complete dislocation. These two partial dislocation can merge together to complete dislocation, and that is called as cross slip. And this is the width of a stacking fault, If this width is more, then the cross slip will be difficult because these two partial will not be able to merge together easily. Okay, so what is cross slip? The merging of two partial dislocation into one complete dislocation is called as the cross slip. Okay, now this partial dislocation can't move, they cannot move, but this complete dislocation that is obtained after the cross slip can move. So what we are getting, if the cross slip is easy, the two partial dislocations easily merge together to get a complete dislocation, then they can move easily. So the cross slip will be more easier. Okay, and the deformation will be more. So what we get there, that if cross slip is more easier, I mean the width of a stacking fault is less, and width of a stacking fault basically decides the stacking fault energy. So width of a stacking fault is less than a stacking fault energy, that will be more. So a smaller stacking fault width means higher stacking fault energy. So stacking fault energy is inversely proportional to stacking fault width. Okay, so what we got here, if the stacking fault width is less, then the cross slip will be more easier, the merging of two partial dislocation will be easier, and the deformation will be more. So if the deformation is more, then the creep resistance, we can say, will be less. So stacking fault energy is inversely proportional to a stacking fault width, and it will be directly proportional to cross slip, and then it will be inversely proportional to creep resistance. Creep resistance will be very less if the cross slip is more. Now coming to the next, if the material has low stacking fault energy means the width of this is more. So if it is like this, one dislocation partial is this one, another dislocation partial is this one, so this width is there, It is high width, it means low stacking fault energy. Low stacking fault energy. In this case, what will happen? Cross slip will not be easy, cross slip will be difficult. Then, if it is difficult, then the crisp resistance will be more. So, in this case, what will happen? Cross slip decreases and creep resistance increases. Okay, now there are many super alloys, that is like iron nickel based, that is also called inconel, that is iron nickel alloy, that is having very good creep resistance. And why we use nickel, let's come on that. Now we know that material at high temperature application material, if we want to use a material at high temperature, it means it should have high creep resistance. It should have high creep resistance. Then what we need in that? It should have low stacking fault energy. Low stacking fault energy means more width of a stacking fault and cross slip will be less. Now we have inconel, that is iron nickel alloy. It is a creep resistance material. And why we use nickel in iron? So nickel has basically very low stacking fault energy. So nickel has very low stacking fault energy, and when we add nickel to iron, then this iron nickel alloy will have low stacking fault energy due to this nickel, presence of the nickel, and hence this alloy should have high creep resistance, and hence this alloy can be used as high temperature application. So inconel, that is iron nickel alloy, can be used as high temperature application because it has nickel in that, and nickel is responsible for imparting these properties, that nickel has very low stacking fault energy, and hence this alloy will have low stacking fault energy. And if it has low stacking fault energy, then cross slip will be difficult, and hence creep resistance will be more. So this is all about this stacking fault. Thank you very much.